reactions it supports, and Larson said it was a fixed support. So what do we want to find here?
The reaction, so AY, A sub X, and the moment of A, about A.
Right. Good. Okay, so let's make a table now. So we're doing the whole problem anyway. So Eugene, what are the forces that are present here? Oh, we left one force out already. We're going to do it. We'll do it anyway. Here. So what are some forces that are present?
Weight.
Okay. Do we know its magnitude?
Yeah.
Yes. Do we know its direction?
Yeah.
Okay. What else?
The node at the end of fourth.
The reactions at A?
Yeah.
So what are they? It's AX,
We don't know the magnitude.
AY, and MA. So we don't know the magnitude of any of them. Do we know the direction?
Yeah.
Yeah. What else is present?
The load.
Hmm?
The other force. 60.
Right, the force due to the distributed load, right? So we called it F up here, so F. Do we know it?
Yeah.
Do we know its direction? So how many unknowns do we have? Eugene?
I can't see the 3.
3 unknowns. How many equations do we need?
3.
And how many bodies?
1.
1 body. Okay, and what body do you want to do? Hmm?
With the whole thing. I don't know.
The beam, right? We want to do the beam? Okay.
So for that moment, you can just assume you know the direction.
Yeah, and again, if you drew it this way or this way, it doesn't matter because we still know it's about the z-axis, right? Say it again.
You said you just draw a positive, and so by drawing a positive,
Right. I tend to draw positive, so if I get a negative, I know it's going in a negative. Okay, so we want to draw the beam. This is point A. This is 3 meters. 3 meters. I don't want to draw the triangle anymore because I know what it reduces to. I know the force F is equal to 6,300 newtons, and I know it's over 1 meter. Isak, what else do I have to draw on here? What other forces and moments?
I just got back from getting water.
Oh, okay. Sam,
The weight,
got the weight, and what's the value of it?
275 kilograms.
What is it?
275 kilograms.
Is that it? No, that's kilograms, that's mass.
Oh, so, yeah, okay.
No mass.
So 20.
Don't screw us up. That's why I always convert it. What did I get?
2695.
2695 newtons. If you want, when you get the problem, right, what did I do? First thing, the mass is this, I converted the weight, cross this stuff out so you never look at it. So you never say it. Okay, what else is there, Sam? What else do I have to draw?
The AX, AY, and
AX, AY, and?
MA.
And a moment about A. And I drew a positive. So I have 3 unknowns, right? I need 3 equations. Which equation do you want to do first? Jose? There's a really easy one.
AX.
That's not an equation. What's the equation?
Some of the forces in the X.
Sum of the forces in the x equal AX, which equals 0. Very quick. We notice now that everybody with me? That fixed support is not taking any X loading. It's not resisting any X loading. What next equation, Jose, do you want to do?
Let's go with some of the forces in the Y.
Some of the forces of Y. Why did you choose that one next?
Because all the forces are going down.
Right, so AY, there's only one equation, minus 6,300 minus 2695 equals zero. So AY turns out to be
89.95.
8995 newtons.
Yes.
Yeah,
You didn't label your axes.
thank you. I got out of practice because I didn't have you draw free body diagrams. I wasn't taken off for any axes. Okay, what? Okay, last moment. Last moment equation. I want to do some of the moments about A. This is a place where people mess up. Everybody's all ears and all eyes.
Yes.
If I'm trying to find the sum of the moments at A, and somebody stuck a screwdriver in there and spun it, am I experiencing that moment?
No.
Yes. Moment A. You gotta put that moment in there. The only time something doesn't isn't in an equation is if a force goes through a point that you're calculating moments about. But a concentrated moment, I'm sticking this in and I'm turning it, it is experiencing that moment. You've got to put it in the equation. Everybody got that? Okay, then I have the 2695. Jason, times what? 2695 times 3, positive or negative?
Negative.
Negative. And then the 6,300 times
5.
5, positive or negative?
Negative.
Equals 0. And MA turns out to be 39585. 39585 Newton meters. Rachel, what was your question?
I was wondering why it wasn't at 6, but I saw that the force was over 1.
Yeah, it's over 1, you know, so this is 5. And this may be where, you know, Jabin said, put 5 here. You know?
I'm just having a hard time understanding how that can be positive when all the forces are trying to make it negative.
Good question. Okay, so let's talk about the physical part now, okay? So here's your, come on up here. Come on down. Big arm out. This one. So I'm pulling down here, right? I'm pulling it down here. So I'm causing a rotation that's what? Negative or positive?
Negative.
Negative. I'm causing a negative. But what does her shoulder have to do? It has to resist it. So I'm pushing this down and creating a positive moment here. In order for me not to rotate it, your arm has to hold up a 39,585 moment here. It's I don't, you know, I never heard of the term restoring, but it's the resistant. It's resisting. So these forces are pulling it down. And the only way that it could be in balance is if this is being twisted that way, the opposite direction. Got it?
Yeah. Yes.
Okay.
I got it.
Okay, good. Okay, so we're really out of time. We never got to my other problem. So let's look at it. Can we just look at it? Okay, so what is this line here? A cable. It's connected to the bottom of B, right? What about this? There's another cable connecting to the middle of A. What is the force between A and B? Normals. What's the forces between A and the surface? Normals. What's going on here at O? It's a pin. It could resist a force in the X and Y. So if I drew a free body diagram of this bar, what would I draw? Free body diagram of this bar. I have a P. I have a tension 1. I have a tension 2. I'm not going to put in distances for being quick. And what am I going to put down here at the pin? OX and OY. If I draw A, what do I draw? Let's assume there's a weight. I have a normal coming from the surface up to A, right?
Yes.
What else do I have? A normal down from B. Remember we did a problem similar to this already. What else do we have? I have which tension coming out? T2. This is T2. This is T1. I also have a weight that's drawn like that of A.
Yes.
And then if I drew a free body diagram of B, I would have the weight of B, the normal from A to B. I have the tension 1, right? So I could really have 3 different free body diagrams. If I drew a free body diagram of A and B together, what would cancel out? The normal between them. So I would still have normal A, I would still have weight A, I'd still have weight B, I still have tension 2, I still have tension 1. The only thing that dropped out was the normal between them.
Yes.
Okay, what if I drew a free body diagram of B, A, and the pole? I would have, so I connected all 3 together. The only thing they're separated from is what? The ground. So what do I have to draw in here? Normal A only. What else? OX and OY. P. And the weights. It's really important to be comfortable doing this, putting 2 things together, putting 3 things together, taking them all apart, because you get to decide which free body diagrams you want. If we look at this problem, what do we have to find? Block saying we weigh this, they're giving us the weight. It rests on a 30% incline, attached to post, has a P, assume all the surfaces are smooth and that the chords are parallel, determine, you only have to determine P. That's all they want. But how many forces are here? OX, OY, T1, T2, P, NA, NAB, weight A, weight B. We have 9 forces in this problem. But the only one they want me to find is P. But there's a hell of a lot of unknowns. We don't know T's, we don't know OY, we don't know OAX. We don't know this normal, we don't know this normal. So we want to try to minimize the number of unknowns that we're using in our equations.
And that combined force body diagram with B and A, did you just leave out the P's because it cancels out?
So here's the combined, you mean this one?
Yeah.
When I combine A and B and the post, I left the tensions intact. If they were intact, the tension is internal to the system. Right? So what would I do to try to find P? You're gonna have to do you're gonna have to look at a lot of free body diagrams. I think this is a really good practice problem. You want me to give you the solution? You want me to email the solutions to that?
Yeah.
Okay, I'll find it. Okay, tests, I gotta get tests now. So, Eugene,
Is that like a all?
Aaron,
This one?
Chris,
Yeah, I don't know what this is. It keeps like moving around. It wasn't there at first. What?
It's like probably just
Yeah.
skin. Like you use your phone and then is that like
No, like to put it on, like.
hey you guys, the Tuesday that we get back from spring break, we always have quizzes on Tuesday. How about we do a setup problem? A setup problem? A 2D setup problem. And I may ask you to draw free body diagrams. This might be what I do. is ask you to draw a free body diagram of things that are separated and together. Did everybody get that? This might be what I give you a free, not this exact one, but a free body diagram of this where you separate things and put it together. Or a quiz on setting up a 2D problem. And homework, the 2D equilibrium